Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I should start off just giving a sense of where we were and see if there are any lingering questions. So some things we talked about last time, the basics of symmetric encryption. That's what we're going to be talking a lot about before. Encryption where you have the same key for encryption and decryption. We talked about stream ciphers like RC4. We talked about block ciphers, in particular Feistel ciphers. We showed how DES worked and got a good look at that. Today we're going to start off with AES. AES is really the block cipher that is used almost everywhere today. It came into being a little over a decade ago. The data encryption standard, which we talked about last time, was, I think, 1974 is when it first was published and standardized. And it became a little old and tired. There were much better choices available. And there was an extensive competition held just before 2000 to find a new block cipher. NIST ran this competition. They didn't know what would happen. They thought they might put out a call and people would say, yeah, right. Why should we go to the trouble of developing a cipher for you? One of the conditions was the cipher that was selected as the winner had to be placed in the public domain. And there was a lot of concern. Well, why would anybody go to a lot of trouble, build a cipher, and then not get anything out of it? But it turned out that when they went through the process, there were 15 submissions. Some of them a little questionable, but most very interesting, and some very good ones. And the process wound up with 5 finalists. I'll talk about them a little bit, and we'll focus in on the winner eventually, which is the middle one here, Rijndael. But the first two were, in some sense, the heavyweights, right? This is IBM. IBM had done the data encryption standard DES. That was sort of the big start. They seemed to have a big advantage. Mars was about the most heavyweight, most heavy cipher of all of these. What happened was several teams within IBM wanted to be the successor to DES. And these several teams wound up getting combined, and they took various elements of each of their original ciphers and cobbled them together, and it really did look like a camel. And it was discovered very late in the process that Mars did not meet its own design requirements. And that kind of killed it. It was already a problem, but it had a huge substitution box. One box, if you get an input that looks like this, here is the output. And most block ciphers have some sort of a substitution box process, or many of them. This was an enormous one. It was generated according to various criteria, and it turned out somebody looked carefully at their big substitution box, and nope, it didn't meet the criteria that they claimed a substitution box should have. So that kind of killed it. RC6 came from RSA. Ron Rivest was heavily involved in its design. It was a very interesting cipher, and it came at exactly the wrong time. Or more appropriately, it met conditions. It was ideal for conditions that existed right around 1997, 98, that didn't exist before and haven't existed since. The thing that it tried to take advantage of is if you want to make a good block cipher, you have to have something that's going to scramble things up really well. Somehow, somewhere, there's got to be a lot of scrambling. And if you want it to be efficient, you want it to scramble a lot. And they looked at what was available on most architectures, and they found that the best scrambling function was a multiplier. And they said, OK, we're going to take advantage of some newer processors are starting to have 64-bit multiplies. This is a good thing, and we can do it. And they work. There's a lot of hardware thrown at it to make it fast. OK, let's take advantage of that. Let's do some really big multiplies and get some really fast scrambling. It was an interesting design. It worked well. Didn't work very well on small processors, on RFIDs and things like that. But it was a gamble. And that was kind of the last time we saw 64-bit multipliers, commonplace in processors. It was decided not long afterwards that it just wasn't worth the hardware investment and all the transistors. And even for a while, 32-bit multiplies were scarce. But they're pretty common now. But 64-bit, not so much. So without that, RC6 really didn't perform very well. I'm going to skip down to Serpent, which was a very innovative design and in many ways the strongest cipher out there. This was designed by some very strong people in the field with very good reputations and was designed with a very good security margin. They didn't want to be close to the edge. And that's what wound up killing it. Because with the security margin that they built in, it wound up being slower than other competitors. Not that much slower, but slower. And this was a bit of a problem when all of them looked secure. Nobody had, came anywhere close to breaking any of them. So this, they were all secure, and this one's slower. Well, yeah, but you could cut down the number of rounds in half in Serpent, and it was still secure. That wasn't the case for any of the others. And there were some pleas with the authors to say, can we have a mode where it has fewer rounds so that it'll be competitive? And they were very insistent. And no, we want a good security margin. And for that reason, it didn't survive. And the final one I'll mention is Twofish. Bruce Schneier, Niels Ferguson, who's in Windows, were amongst the designers of this. Very clever, very nice, did a lot of tricks. And by most accounts, because these two kind of imploded and because Serpent was regarded as too slow, Twofish had no obvious weaknesses, and it was probably considered by most the runner-up in this. But there's no official basis for that. But a very nice cipher, and people still use it today. Even though since it wasn't the winner, it wasn't required to be in the public domain. It has been placed in the public domain, and therefore it gets a lot of use.
Any relation between Twofish and Blowfish?
Oh yes, there are different ciphers. Yes, Blowfish is an earlier cipher that was done. Bruce Schneier was part of it. I don't remember if there were others that were part of it. But Twofish used some of those principles, but it was a much larger design team and a lot of new things in it. The biggest thing in common is the fish in the name. Sorry. But OK, let's talk about Rijndael. Rijndael was the winner. Rijndael, as the winner, is now AES and is a very interesting, very strong cipher. Most of these also, most ciphers out there follow the Feistel design that I talked about last time as a very easy way to construct a cipher that is invertible. Right? Invertibility is the hardest thing to achieve. Rijndael does not use that. So let's take a look at what Rijndael does. Rijndael takes either 16, 24, or 32 bytes of key. It's also designed to take 16, 24, or 32 bytes of input data. However, AES only required 16 bytes. So the AES specification says Rijndael with 16 bytes of data. So you can sort of ignore this when we're talking about AES. It will then arrange the data in this sort of block form. So each of these blocks is now a byte. And think of this square form. It's sometimes called a square cipher. It goes through a few steps. First of all, it goes through a bunch of rounds. This round length, 10 rounds, is very close to the minimum security margin. Right? We have seen there are theoretical breaks of Rijndael, and a theoretical break means tiny, tiny weaknesses have been found up to 7 rounds. So 10 rounds is not that much more than that. Now, that doesn't mean it's a useless cipher at 7 rounds. It just means theoretically it doesn't have the 128 bits of security that you would like it to have if you're using a 128-bit key. So AES at 10 rounds, OK, it seems good. Go up. If you increase the key length, the main benefit you're getting is more rounds. If there are more key bits, you think you get more security from the more key bits, and you do, but that's not, in this case, really it's the extra rounds. The 128 bits is enough. It's the number of rounds that's really the edge. And a lot of people suggested at the time that this was a fine cipher, but it should be more like 16 rounds here, 24 rounds here, 32 rounds here, and give it the same security margin as Serpent. And if it had been done, it would be very comparable with Serpent. We'd have very good security margins, and maybe Twofish would have won because it was faster. I don't know. OK, so this is the way it's spec'd out, and this is the way it works. Each round has 4 steps. And the 4 steps are all pretty quick and simple, and I'll tell you what they are. The first step is a byte substitution step. So what you do is you have an S box, a table of 256 possible byte substitutions. It's a permutation. If you see this byte, change it to that byte. And it's just an array of 256 values. That's the substitution box, the S box of Rijndael. And all you do is you go through this square, and you go through and you just change each byte according to that table. Okay? 16 changes. The next step is what's called shift row. And what you do is you start rotating these rows. Now, OK, I worked way too hard on this slide. I had this vision of a slide that they'd shift and they'd move around and that. I'm not that good a slideware engineer. It's not worth it. But you could sort of see how this happens. Basically, this row rotates 1 position, 2 bytes, and 3 bytes down there. OK? And that's all it is. Very simple. Step 2. Step 3, so that's how it winds up, OK, if you couldn't see it before. Step 3 is a linear transformation on each column. So think of it as sort of like you're taking the columns individually, and you're putting them through a matrix multiplication. But I use this kind of funny symbol because it's not ordinary matrix multiplication. This is matrix multiplication in a Galois field. And I'll talk a little bit more about Galois fields later, although I promise I won't explain what they are unless you really, really want me to, and I don't think you do. But it's sort of a funny kind of multiplication, but it looks kind of like matrix multiplication. And if you multiply, for instance, a matrix times a vector, you get a vector. So it effectively just goes through each column, multiplies that out, and then the thing it does is this matrix multiplication. Remember the way matrix multiplication works. This times this, plus this times this, plus this times this, plus this times this. And that winds up going up top. So you get effects of all of these bytes mixing into there. And all of these bytes also mix into here and here and here. And you go through and get all that mixing. And then you go through and you do the same thing there. You do the same thing there. You do the same thing there. And that's the only thing that, after the byte sub, has really scrambled any of these bytes at all, other than sort of moving them around. There are principles in cipher design, which are sometimes described as confusion and diffusion. Diffusion is moving things around, and that's sort of the rotate stuff. The confusion is the little bit twiddling stuff that's being done. And here we're getting some confusion. OK, the final of the 4 steps is, well, notice ciphers are supposed to have keys, right? We haven't actually used the key at all yet. And the final transformation, the final step, is just take what you have now and literally XOR in a key. Nothing more than that. 16 bytes of key, 16 bytes of data, do a big XOR. Wham, done. That's the extent to which the key is used. The only thing that's a little complex here is that for each round you use a different key. And there is a key schedule. It's complicated. I don't want to spend time describing it. There's also a lot of Galois field mathematics in the key derivation schedule. But it's a lot easier than the other stuff because unlike the other stuff here, all these steps had to be reversible. A key derivation doesn't have to be. You have the same key to decrypt. You go through from the initial key and you derive the same subkeys the same way each time. So it can be a very complicated, and it is in this case, very complex looking kind of operation, but it's not that hard to get something that's invertible. Like all of these 4 steps were invertible. So it makes sense that the key derivation doesn't have to be invertible, but anything that's done with the key or with anything else to the data does have to be invertible. And that's where you have to focus the attention. Okay, so in practice, Rijndael is used more and more for a lot of reasons. It's fast, it's small, it works well on big processors, it works well on small processors, works well on hardware, works well on software. It was a good overall choice. People are very happy with it. It does have a lot of mathematical structure, and that structure has been thought might become a weakness at some point, but so far people have found things that might suggest weaknesses, but nothing really substantial. But one thing that's getting a lot more play and a lot more use is the AES-NI instruction set, which has made it into newer processors. Basically does a whole round, all 4 of those steps, as one machine instruction. So when you have that, it's not one cycle, but it's still pretty fast. When you have that, you can go through an entire AES encryption or decryption very, very quickly if you have modern hardware. So it's becoming very popular for that reason as well. Okay, so AES aside, you know everything about AES now. I'm going to talk a little bit about how you use a cipher like AES. And when I say like AES in practice, I mean AES, because that's what we're using for block ciphers. So when you have this nice tool available, what do you do with it? Well, the first thing you might think of is you take your input data, you've got a book you want to encrypt, you've got some big important data set. And AES takes data 128 bits at a time and encrypts those 128 bits and gives you a 128-bit output. So what do? Well, the first thing you might want to do is, okay, take the first 128 bits, apply the cipher. Take the next 128, apply the cipher. Keep on doing that, just go through everything. And that can work all right, but it leaves you vulnerable to some attacks. One thing you might notice is that if you have the same input, you're going to get the same output. So if you have some maybe structured data, somebody watching can see, oh, this output's the same as this output, and I have a guess as to what this might be, so now I'm pretty sure I know what this is. And you can start doing a little bit of analysis there. It's not a huge amount. It's also subject to reordering. It might be that this is data with, you remember the payment example we had last time where somebody with a stream cipher could flip 1 bit? Well, you could take a full block and substitute another block, maybe from here, reorder things in ways that might change the amount. Maybe there are 2 blocks, that's the payment data, and you switch them around, and suddenly now this was all zeros and this was a small payment, and now the high order bits of the payment move up here, and you've got a problem. Or the person making the order has a problem. You, having switched it around, probably have a lot more money than you were supposed to. Okay. So reasons not to use this. Even though it's very simple to do, you just run the inverse cipher to invert it. It's not a problem. But we really want something better than that. So what we generally do is we see that identical blocks give you identical encryptions. That's what I just said about reorderings, give information. There's passive observer information. So instead, we prefer other modes. And by far the most common mode, and the one that if you're doing things now that we want, we the crypto board want people to use, unless there are exigent circumstances of some sort, is called cipher block chaining. And cipher block chaining is just using any block cipher and adding one additional XOR to the work for each block that you put in. And it's a pretty simple thing. All you do is you start off with some IV, and the IV should be different if the key is staying the same, because if you have the same key and the same initial value and the same first block, then you'll get the same first block of output. And an observer could see that. So if the key is staying the same, the initial value should change every time. And it could change just by being randomly picked. This can be completely public. It's what used to be called SALT for any old-timers out there. So you have an initial value, you have a first block of data, you exclusive OR them, you put that through the block cipher instead of just the raw value. And you take that output and you XOR that with the next block of input before it goes through the cipher. And what this means is that even if this block and this block of input are the same, this is going to get XORed with stuff here, and it's going to get XORed and output and XORed and output and XORed again. There's going to be something completely different that goes in here and something completely different that comes out there. So you've got things scrambled up very nicely. You've also got things tied together. You can't just swap two blocks and have the effect that those two blocks of input are going to be swapped, or even swap in something from somewhere else, because everything is chained together. Now, decryption is pretty simple here, too. You just run the cipher backwards, and you just take the XORs from here, XORing again. The same trick of XORing twice that we've used before gets you back to where you started. So if this XORed with that went in here, then when you come back up here and you invert the cipher, all you have to do is XOR with that, which you still got around, and you get that back. So inverting cipher block chaining works pretty well. So it all goes very nicely. Now, some people say that CBC mode, cipher block chaining, isn't good for one of a couple of reasons that are actually myths. So I want to show you a couple of myths, a couple of nice little tricks here. First myth is I don't want to use CBC because I need random access to the data. It's all chained together. I've got this 12 gig block of data that I encrypted with one key. Well, that's an awful lot to do as one block. But OK, there's 12 gigs of data there. And now I need to get random access to it. I don't want to use CBC because then I'm going to have to go back to the beginning and decrypt. Not true. Let's take a look a little bit more carefully at how this works. What do I need if I want to decrypt just these two blocks down here? So here's somewhere in the data, 2 blocks. I want to decrypt that. Well, I can get rid of all this. The only thing I need to do that decryption is the previous block of ciphertext. I need that to come up here. But I don't need to decrypt the whole thing from the beginning. So you really can. Yes, you encrypt sequentially. You can't encrypt in pieces. But you can decrypt just a small piece of the data, and it all works just fine. OK? Oh, I had an animation I've forgotten about. Isn't that cute? That becomes the IV for this. And everything works. And you could just run this as though this is ordinary CBC decryption now with this as the IV. Just use the same routine that you had before. OK, so that myth has been dispelled. So let's look at another one. CBC is terrible because of data expansion, right? Well, it's not just CBC. This is a problem for any block cipher because you have to pad it out. Suppose I've got an application where I've got 37 bytes of data in this field, and now I'm told I've got to encrypt it. And, well, you have to do whole blocks, right? And maybe that field is hard-coded in, and I don't want to do that, so I'm going to go back to a stream cipher because I can encrypt bit by bit with the stream cipher. Well, you can also get rid of that data expansion in almost all cases with a block cipher using CBC with a little trick. It's a very cute little trick that is surprising that it works. So there's something called ciphertext stealing. And it comes from the observation that if you've got data that you've encrypted in CBC mode, and you had to pad out the end because there's some useless stuff out here, your real data only went this far, so you just put in some zeros at the end, or anything, but let's just say that you padded with zeros. Then it turns out that you can take the same number of bytes here that were padded and just discard them from the second to last block, the penultimate block of ciphertext, and you can still recover. So just throw it away. Now you've got ciphertext here that's exactly the same size as the plaintext. Throw it away, and let's see why this works. Suppose I have to invert, and I'm missing that. Well, I can still invert this, and I get some value here from just running the inverse cipher on the last block up through here. I get that. This gives me a value. I know that this value here was supposed to be all zeros. So now I can figure out exactly what this must have been to XOR with that to make all zeros, namely exactly what's up there. So now I know what's missing, and I can go and just decrypt everything as normal. So I do that. I turn that, whoops, there. I put that in there, that turns that to zeros, and I can decrypt. Okay, so this is a trick. I said it works almost everywhere. It works as long as you are using CBC mode with more than one block of text. It doesn't work on a single block because you can't delete the thing before this. There's nothing to delete there. So yes, you do have to have at least one block. But you can still make it pretty tight. Okay, so CBC mode works pretty well. We like it a lot. We use it a lot. I'll talk about some other modes later on. But that myth has been dispelled. Okay, one other mode I want to talk about quickly that comes up a lot, and it'll come up later, so I want to mention it, and that is counter mode. It's kind of an odd thing. You would think you don't want to ever do this at all, but I'll describe now why some people like to do it, and it'll come up again, I promise. So the idea is we just take whatever key we're using, and we just encrypt 0, then we encrypt 1, then we encrypt 2, then we encrypt 3, and you can see what comes next. And that will form some output. And that output we will use as a key stream and just XOR it with the plaintext and get ciphertext. So what we're doing here is taking our nice, big, robust block cipher, and we said we want to use block ciphers and not stream ciphers because stream ciphers have all sorts of vulnerabilities, or not so much vulnerabilities, but fragilities that can be used very carelessly, that can be misused very easily. And we have turned this nice block cipher into a stream cipher. Well, why did we do that? We were willing to accept the difficulty and slowness relative to a stream cipher of a block cipher to get rid of that fragility. And now we're going through all the work of a block cipher, and we're getting a stream cipher here. Right now, if I flip one bit of ciphertext, then I know that that will flip exactly that same bit of plaintext, and you can start playing tricks with it. You have issues with using the same key, gives you, vulnerabilities and problems. Well, it turns out that although stream ciphers are fragile, they can be used well if they're used properly. They do have some benefits. And I'm showing you this now because I'll bring it in towards the end of today as sort of the modern way, the modern block cipher mode. But before I get there, I have to talk more about cipher integrity. And if you have some data and you want it integrity checked, then the traditional method is, well, you add some sort of a checksum, right? That's what you see on the last digit of a credit card, or lots of places. You just add one block of something, one byte, one digit, whatever, as a checksum to guard against some transmission error or some careless error of some sort. Now, checksum is a really good way to prevent accidental disruption of data, something getting corrupted in the network. It's a terrible thing to use in a security context, because people understand how a checksum is supposed to work, and if they're going to change some block of data here, they can just make a corresponding change to the checksum and make the checksum the right checksum for whatever they want to change the value to. So for cryptographic integrity, we need something better. We need something that can work against an adversary who actually knows what's going on. So what we use here is something that's used everywhere, a hash function. And the hash function turns out to be kind of the hammer in the cryptographer's toolkit. It's used for lots of things. And all it really is just a function that takes arbitrary length data and gives you a fixed length output. That's sort of a fingerprint of this data. It'll always be the same for that data. It's sort of something that stands in for that data. And it is supposed to be difficult to invert. And I'll explain what that is, what that means in a second. But there are actually several properties that we have of these one-way hashes. And it used to be that we blurred them all together. But we've discovered they're all very distinct. They have very different properties and very different assumptions behind them. So this non-invertibility turns out to be the assumption that we start out with, that if you have the output of a hash function, you shouldn't be able to find the input. It also turns out that that is the weakest assumption, because we use it in other ways with stronger assumptions behind it. Another thing that we like to get from hash functions is what's called resistance to second preimage attacks. And a second preimage means if I give you an x, can you find an x prime that has the same hash value? Now, how do these two relate to each other? Well, if you have this, then you certainly got that. Because if you could invert, then you could just find this. Something that should be clear at this point is there are lots of collisions in a hash function, right? You're taking a big data set and turning it into a small data. So even if we're hashing 257 bits down to 256 bits, most outputs have a partner. That most inputs have a partner that have the same output. If you have an arbitrary length input, there are probably infinitely many things that'll hit each output. So there are going to be lots of collisions. The question is, can you find one? Well, in this case, if you can invert, you can certainly find collisions, because all you do is, well, maybe when I took h of x and tried to invert that, I got x back. But most of the time, for most inputs, x, you'll get something else back, because there are probably an infinite number of things that have y, and if I can invert y, I get just one of those things. It will match anything in that infinity. So this is a stronger assumption, but there's even a stronger one. That's kind of the gold standard for hash functions, and that is collision intractability. That is that you can't find any collisions at all. This is something that has no practical value. It has tremendous PR value and has some value in our sort of understanding of hash functions. And it's sort of an interesting property that for any good hash function that's out there, and even some bad hash functions that are out there, for the SHA-1 hash function, which I'll talk about a lot more soon, nobody has ever found a single pair of inputs that have the same output. Even though there are infinite numbers of such, there are lots of them, no one has ever found a single pair like that. People have come close. People think they know how to do it. People think that with a certain amount of resources, it would be hard. People think that if we took all that hardware that's out there now trying to mine bitcoins and use that hardware for a couple hours, they'd very quickly find a collision. But nobody has ever found a collision there. So it's still strong in that regard. Now, MD5, the predecessor, I should go back and just sort of hit the list. Here's sort of a list of hash functions that are out there. MD5 was broken about 10 years ago. MD4 and MD5 actually broken together. Broken in the sense that collisions were found. Now, still, even though it was broken 10 years ago, nobody has a clue of how to invert it. But there are collisions, and therefore, we don't want to use it anymore. And if we do use it, then we'll have reporters writing articles about how stupid Microsoft is using a broken hash function, even if we use it in a completely secure way. So we have to avoid it. And the expectation has been for a few years that any day now, any week now, any month now, sometime soon, SHA-1 is going to go in that sense. SHA-256 is a newer, much stronger hash function. I'll talk about that a little bit. And SHA-3 is an even newer, but not necessarily particularly stronger hash function. OK, so here are the requirements. Here's the gold standard. We want our hash functions to have no collisions that have ever been found anywhere. Okay? And we have that still for all the SHAs, but not for the MD set of functions. OK, so these hash functions turn out to be tremendously useful. They're used when we're doing encryption, especially symmetric encryption, as an integrity check. Basically, a checksum, but a cryptographic checksum that you can't muck with, you can't break, because we usually put a key in there. And I'll describe how we do that. They're also used in digital signatures. If you remember the digital signatures we talked about a little bit last time, signing a huge block of data can be very cumbersome. So what we generally do with digital signatures is take that big chunk of data, hash it down to something small, and sign just that. Sign basically the fingerprint and have that be the proxy for that whole big block of data. And as long as nobody can find anything else that has the same hash function, we really are signing that. Signatures break horribly if we start getting collisions, including second preimage is enough there. You don't have to be able to invert to make a mockery of this characteristic. And a third characteristic that we take advantage of is entropy distillation. What we have for all sorts of needs in cryptography and other places, but especially in cryptography, we need randomness. We need really good randomness. And we don't really know how to get really good randomness most of the time. What we do is we get things that look kind of random. And we don't know how much entropy there really is, how much true randomness there really is in this stuff. So we take it and we kind of hope. And to boost our confidence, what we do is we don't just take a random source and say, OK, this is a source that we hope is good and random, then we'll take 128 bits of that and we'll make that a key. What we do is take lots of sources, put them together, put them through a hash function, and get 128 bits or 160 bits or whatever it is, get that out. And that has basically distilled the entropy, because now if we have 1,000 bits that were really biased in bad ways and only had about 200 bits of entropy total in those 1,000 bits of input, and we hash that down to 160 bits, well, now we've got 160 bits of entropy in there, and that's really good. And we can start using that. So this is used a lot. It doesn't particularly matter if the hash function is broken. It's still a good entropy distillation. We use MD5 constantly in this company for this purpose, and we should be getting rid of it. Not because it's bad to use for this purpose, but because if it's used for that, then it somehow creeps in and starts getting used for other things. And some blogger sees we're using MD5, and oh, we're stupid again because it's broken. And it's just, yes, it's not a risk here from a security perspective. It is a risk from a PR or another perspective, which is sometimes as important. OK, so these hash functions have lots of uses. Let's talk about how they're built. So the most common way, just like we had this Feistel cipher design for block ciphers, the most common way of building a hash function is called the Merkle-Dalmgaard construction. And the construction basically is to build a compression function. And a compression function is just like what you would expect on a hash function. It takes a lot of data and produces a little bit of data. But it doesn't take an arbitrary amount of data. It takes a fixed large amount of data and produces a fixed smaller amount of data. And then it's going to get iterated somehow. And it's going to get iterated in a way that looks a lot like what we did about 20 minutes ago for cipher block chaining. It's going to get iterated in this way, where we take the input data, some initial value, put these things through a compression function, and get an output that's the same size as this initial value. And goes through, and we just keep on repeating, and eventually we get through to the output. Okay? Same basic construction. This kind of construction comes up over and over and over again. Okay? So I want to take a look at SHA-1. SHA-1 takes a 512-bit input here. It's going to produce a 160-bit output, and also takes the second input, IV. So the total input is 672 bits. But this is sort of the intermediate block size that goes through. And I'm going to spend just a couple minutes showing you how SHA-1 works. Even though we don't want you to use it anymore, we prefer SHA-2. They look kind of the same, and SHA-1's easier to talk about. So SHA-1, 160-bit internal state here. Did I say that backwards before? The internal state is 160 bits that goes through here. Yeah. So that's what you keep at any time. That's what's going to come through the next time. So you take 160 bits of state, and you have to take 512 bits of input. And it's kind of, if you cook, it's kind of like sprinkling things into a broth. What you do is you take this 160 bits of state, and you just sprinkle 512 bits of input, a few bits at a time in, and you stir and you stir and stir, and then you sprinkle a few more bits, and you stir and stir and stir. And that's kind of the way it works for 80 rounds of stirring. So you take this state, 160 bits, 5 32-bit words, and mostly what's done is shifting. Really, each round is mostly a shift. So let's talk about what happens in each of these 5 words. This word doesn't change at all. It just shifts over. This 32-bit word, well, it gets rotated 30 bits, or backwards 2 bits, and nothing else. That doesn't change. That doesn't change. The only change of any substance, and the only place where any of these bits get mixed in, is down here. And even that doesn't do a lot. So quickly, what goes on there is that final 32-bit transform takes the rightmost of the 5 D words of input, adds the leftmost word rotated 5 bits. So you've got the rightmost word, take the leftmost word, rotate it in, adds that in, does a round-dependent function on the middle 3, dependent on the middle 3 words. I'll show you how that goes. So you take these middle 3 words, and you take a round-dependent function on that, and stuff that in here as well. And here's what the round-dependent function looks like. Depending on the round, it's one of these 3 things. And finally, adds a round-dependent constant, sprinkles in some of the bits that were up over here of the input, just a little portion of that 512-bit message. Just take a byte from here, and a byte from here, and a byte from there. Put those in, put those all together, and stir. That's a round of SHA-1. it goes on for 80 rounds, and you get an output. That reduces one block, that consumes 512 bits of input. You do, for the next 512 bits, you do another 80 rounds. Keep on going. OK. We don't want you using SHA-1 anymore. We want people using the newer hash functions, SHA-256, SHA-512. Well, these look a lot like SHA-1. SHA-256 basically has almost exactly the same structure. It just has 8 32-bit registers instead of 5. That's why it's up to 256 bits instead of the 160 bits before. And it's still all but, on each round, it shifts everything to the right one. All but 2 of the values stay exactly the same other than being shifted. One of the values that goes through some very minor changes, just like that little tiny rotate that was done in SHA-1. And it's only one of those words that goes through some round-dependent functions and some scrambling. Very similar process. SHA-256 is similar to SHA-1. SHA-512 is very similar to SHA-256. Really, it uses almost exactly the same structure. The only principal difference is that the subblocks, the words, instead of being 32-bit D words, are 64-bit words here. And that way you get double the internal state, but everything is structured in exactly the same way. So now you know how SHA-1, SHA-2, both major variants of SHA-2 work. There's something called SHA-384, which is just do this and then truncate. There's something called SHA-224 to be compatible with some smaller things, which is do this and truncate. Nothing more to it. OK? SHA-3 is also something that's come around recently. There was a competition that just finished not long ago, about a year ago, for a new hash function. The AES competition was regarded as so successful that, well, let's do it again. Let's get a new hash function. And the reason was different this time. The first time it was done because we desperately needed a block cipher. People were still using DES because it was the only standardized one, but it was way too weak. It was easily breakable. And people who wanted security were using triple DES, which is run DES 3 times with 3 different keys, which is not that bad, but it's dog slow. Here, a competition was run for a new hash function, but not because there's anything known to be wrong with the SHA-2 family, but more a matter of an abundance of caution here. We use hash functions so much everywhere, and it's been such a painful process, such a slow process to move from MD5 and SHA-1 to the SHA-2 family. It was decided we'd better have a backup, have an alternative ready to go just in case. So SHA-3 is not appreciably stronger. It's not obviously stronger in any way than the SHA-2 family. It's not appreciably faster, but it is different. And that's the benefit. And the idea is that we get it built and get it deployed and get it available and maybe have it used in parallel. For mission-critical applications, maybe you use both SHA-2 and SHA-3 simultaneously, and you make sure that they both match what you're expecting. So SHA-3 looks very different. It uses what's called a sponge construction, which does a large transformation on a large data cache. In the case of SHA-3 in particular, that's a 200-byte data cache. It's pretty big. At least for cryptographic primitives, it's pretty big. And then you take smaller blocks of data, and you just XOR them into the sponge function, and you churn the sponge. So does this remind you of anything? Well, it's kind of this again. The only real difference is these blocks are now big blocks. So here what we're doing is kind of this. The sponge function is this big churning, and you churn and you mix in a few bytes with XORing right on the top. So you just XOR right along the beginning of the data cache. And there's some output that becomes the new input. You XOR that in. You apply the sponge function. You apply the churn, the big churn of the 1,600 bits of data in the middle now. And you just churn and put in a new block, churn and put in a new block. And eventually get the output. And usually you don't want all of this output. 1,600 bits of output in the hash function is a lot. So you just take the first 256 bits or 512 bits or whatever you want of that. That's all it is. And that's really about all I want to say about sponge construction here. Just give you a sense for how it works. Yeah. I don't.
Take ECP mode and truncate it and get a hash function too, right? How good is that?
So, sorry, would you?
The European ECP mode of AES.
Mm-hmm.
So how about the following function? Just encrypt your input using ECP mode and then truncate it?
Well, you don't want to use EBC mode. You want to use CBC mode. But yes, in fact, I will mention that very shortly. You're a couple of slides ahead of me. But that is a common way of doing it. It turns out to be slower because ciphers have to be invertible. And to make them invertible, they tend to be slower. But it is used, and it's used quite a lot, in fact. So we're getting to the end. We want to talk about message authentication codes. This was the first principal use of hash functions. We do this quite a lot with a keyed hash. We use a hash function and just put in a key and our data. And that way, you should know that you're getting what you expect. Basically, you take a secret key and the correct message, and you hash them together. And now if an attacker tries to change the message, the attacker, not knowing the key, will not know what the correct new message authentication code should be. And therefore, it'll be obvious to anybody who is trying to read the data. But there's a question of how we're going to do this. And the but how comes in this form. Suppose we have the data, the message, and the key. Should we, remember, a hash function just takes a big block of data. It doesn't care what's what. Should we take the key and then append the message? Should we take the message and then append the key? Well, it turns out both of these have problems. This has some big problems because of the way we construct hash functions, that you could probably just append more data to the end of this and figure out what the hash should be. So it has what's called a length extension attack. And it turns out there are some attacks on this method as well. So we don't want that used either. What we do is what's called HMAC. This is sort of the standard. And HMAC is a pretty simple thing. It's just an extra layer of hashing. It says hash the key together with the message, and then then prepend the key to that and hash that again. Well, that looks like, well, it's a lot of wasted effort, right? I'm doing 2 hashes when I only need 1. Well, yes, it's 2 hashes, but this first hash might be a big hash if the message is big. But now what you've got here is small. So this second hash is really just one extra iteration of the compression function. It's a small hash. It's not a big deal. And it turns out this has some nice provable characteristics that it meets everything you want. So this is how you do a keyed hash. But still, there's some issues on how you actually use that keyed hash. Suppose we have your original message, and you have an encryption key and a key that you're going to use for your integrity check. And you should always, unless you know for a fact that it's OK to use the same key in both, cryptographic, basically sanity checking and hygiene requires use separate keys for separate purposes. So you have an encryption key and you have a MAC key. So how do you integrity protect your message? There are a few methods out there. One is usually known as encrypt and MAC. You encrypt the message, and you put a message authentication code on that same message, and you send the 2 together. There's also what's called encrypt then MAC, which is encrypt, take the encrypted message, take the ciphertext, and put an integrity check on the ciphertext. And the third is MAC then encrypt, which is basically you put a MAC inside the message, inside the thing that you're going to encrypt. So you take the message, you put a MAC on the message, and then you encrypt the whole thing. Well, turns out there are various use cases, various advantages, disadvantages, but almost always this turns out to be best. I don't want to spend a lot of time going into why. Not always, but almost always. And this is sort of the standard rule. This is, sometimes you hear the, do you encrypt then MAC? Do you MAC then encrypt? Well, usually you want to do this. But usually isn't always good enough. So what we really prefer is having authenticated encryption. And this is sort of the new fad in symmetric cryptography. There's a lot of this going around now. If there's a disease, this is the disease that people are catching. Because this is what people want to do, right? They want their data to be secured, both from a confidentiality standpoint and an integrity standpoint. That's the standard use. If you're not thinking about it, if you don't know what you're doing, you want that done. And you don't want, okay, well, I do this, and then I do this, and I put these together, I get these two keys, and this. We want a single primitive that will do this as efficiently as possible. So let's go again and take a look at our block cipher modes and see what we can get out of this. Well, the first thing I'll mention is CBC MAC, which is exactly what you were suggesting we have. This is a common way of doing a MAC, even though it's not the most efficient. It's still pretty good, which says you basically take a key, you encrypt your data, and you just take the last block, and the last block is your MAC. And as long as you're using a different key than what you use for encryption, well, then this is fine. You don't need all of this stuff because you don't need to decrypt. You're just going to do an integrity check at the end. Okay? So here is one of our authenticated encryption modes. There are a whole bunch of them out there now, but CCM is a popular one. Niels Ferguson was also involved in the development of this. And what CCM does is basically do CBC MAC. Remember I talked about counter mode for encryption. Counter mode, well, this terrible thing, turning a block cipher into a stream cipher. Well, it turns out that if you use that and you use CBC MAC, then you're using basically the same block cipher for all of your operations. You don't need a separate hash function and a separate this. You can use the same key. Basically, you just put them together, use both of these together, and everything works well. Okay, it's good, but it's a little slow because you're using for your authentication this CBC MAC, which is a little bulky. So the thing that's most popular today is what's called Galois counter mode. And Galois counter mode does, and I think this is the last slide of substance here, uses counter mode again for encryption, but instead of going through this whole added layer of encryption, running a block cipher, which is churning, right, 10 rounds of AES, 12 or 14 rounds of AES, whatever it is, to do each block, it's doing something called Galois multiplication. And Galois multiplication, or Galois field multiplication, basically it's just doing one multiply per block and zipping through the blocks, doing something very, very quick. Now that Galois multiplication could be a little painful in software, except that it's very fast in hardware. It basically looks a lot like multiplication without bothering to do any carries. So that should be faster, except the multiplication in hardware typically does carries. But newer processors also, along with the AES-NI instruction, have this instruction, which is affectionately known as pickle muckle duck. And once you've heard it, you cannot forget it. Which is basically perform carryless multiply on quad words, 64-bit words. It does this special Galois multiply, which is very fast in hardware. and zips right through, and you can get an authenticated encryption very quickly. Okay, so I've pretty much used up my time. I can say a little bit about what's coming next. Next time, 2 weeks from now, we're going to be talking about asymmetric functions, Diffie-Hellman, RSA, how RSA and Diffie-Hellman actually work. And you can really, 10 or 15 minutes from scratch, you can understand RSA. Not a problem. And then we'll go on to elliptic curves and lattice-based stuff, protocol properties, and other stuff coming on. Okay, I kind of raced through this. I wanted to get through to authenticated encryption, so I rushed a little bit. But anyway, any questions? That's it. So yeah.
I want to ask about the impact of truncating. You talked earlier about doing SHA-256 and truncating part of it.
Yep.
Is that still as secure? What are you losing when that happens?
You definitely lose security. The only reason for doing it is space, because you're doing all the work. The more bits you truncate, the more likely it is that there'll be a collision, right? Imagine SHA-256 truncated down to 128 bits. Well, truncated, 128-bit hash function just on its length is considered insecure. And the reason is, and maybe I should talk about this more another time, but most of you have probably heard of the birthday paradox. And the birthday paradox says basically if you get, I can't remember the number now, is it 19? I think it's 9.
It was 13.
It's square root of 365 plus or minus 1, basically. But if you have square root of 365 possibilities, then that's enough that you'll get a repeat, right? So if you get about 20 people in a room, and we could do this, we have a little bit more than that, it's almost a certainty that at least 2 people in the room have the same birthday. And if we were in an elementary school class right now, we'd go through and have everybody say what month they were born in, and we'll find the collision. I'm sure there's got to be one in here. But with a 128-bit hash function, you only have to go through 2 to the 64 possibilities before you get 2 inputs that have the same hash. So for the birthday paradox reason, 2 to the 64 seems like a big number, but it's not that big a number. It's not ridiculously outrageous. We really want longer. 160 bits for SHA-1. Okay, 2 to the 80, that's kind of beyond the edge, but not that far beyond the edge. So even the birthday attack gets, breaks SHA-1 in a not unreasonable amount of time. And there are some slightly better attacks that are available. They just haven't quite been implemented and used. We really want a much longer hash function just to resist against birthday attacks. And if we go down from SHA-256 to SHA-224, then it's only 112 bits of security against birthday attack instead of 128. But that's the only weakness. Nothing but bit length. Yep.
So there perf issues running SHA-512 on 32-bit processor?
Yes, very much so. If you've got a 64-bit processor, it's much, much faster. So your function of choice depends on your processor size, absolutely. You can do it, these operations don't require a lot of 64-bit manipulations. It's not 64-bit multiplies and such. So you can do it with, you can simulate a 64-bit value with 2 32-bit registers, but that means twice as many registers to muck around with, and yes, the performance, there'll be a big hit. Okay.
So a while ago I heard that generally to prefer AES 128 over 256.
Okay, so yeah, let me give a little bit of a sense there. I think basically our feeling is AES 128 is just fine, no problem, feel free to use it. You get a few extra rounds if you go up to AES 256. It goes from 10 rounds up to 14 rounds. That adds some security. You would think you also get extra security from the extra key length, and there is some. But it turns out that it's been discovered there are some slight weaknesses in the key schedule of AES 256 that make it not quite as strong as you would expect a 256-bit function to be. It's still regarded as stronger than AES 128, but there's a sense of it's stronger, but AES 128 is really plenty strong for all our applications. There are some weaknesses in the 256-bit version. Why use it? Many people use it anyway. I'm not going to tell you not to, but I don't see a big advantage to using it. Yeah.
Different number of rounds for AES 128, 256, 512. But when we were talking about short 256 and 512, the number of rounds stayed the same, 80.
Yes, I think I've got it right. I think, well, I think that the SHA-2 functions actually have only 64 rounds, in fact. I think SHA-256 and SHA-512 do the same sort of thing, but if I recall, they're both 64 rounds, but they're somewhat more complicated rounds. But it's true, you don't get that much more round security. SHA-256 and SHA-512 are almost exactly the same function. It's just on double the data, and you get those benefits.
Is the IV standardized for SHA functions?
Yes, yes. The IVs are fixed. You can look them up. They come from mathematical constants, and the standardized use is only valid with these particular IVs, so that you know exactly what you should get. Yeah.
Isn't the recommended encryption mode a CTR? But does CTR have equivalent security to CBC?
CBC is the recommended.
No, you said CTR, right? In the final slides, you said normal for practice.
Okay, so what we prefer, what the crypto board prefers, Microsoft standards, is CBC. CBC encryption with separate authentication. That's sort of common and standard. The authenticated encryption modes are new. Some people are saying, hey, this is new, I want to use it, it's available. We're not going to complain if you want to use one of the authenticated encryption modes, CCM or GCM especially, and they're sort of being rewritten into the SDL rules to say, okay, if you want to use those, not a big deal. Those do use CTR for encryption, but they use it in a way that's carefully managed. Stream ciphers are, basically CTR becomes a stream cipher. It takes a block cipher, makes a stream cipher. There's nothing wrong with stream ciphers when they're properly used. They were for years the most common form. When you did TLS negotiation, you usually did it, and still, maybe it's 40% of the time now, you're using RC4 as a stream cipher. In a properly managed environment, it's fine. It's just there have been so many cases in this company and in other places where we've messed them up that we're saying, don't use them on your own. But in this context, it's used within a managed environment where it's used in this particular way, so it's okay. Yeah?
I've heard there are ways you can misuse GCM. Could you talk to that?
Not very well. I've heard some of this. I should look it up more. I'll tell you what. I'll take a look and try to get some data for next time. But I've heard this also. I think it's not a realistic case, but yeah, I should know. Yeah.
You talked about random reads working properly for CBC. Mm-hmm. What about random writes? Obviously, that won't work.
That
for CBC.
That does not work.
So what does BitLocker use? Right? BitLocker obviously has random writes on a vast scale.
Yes.
What do they use in situations like that?
BitLocker has some interesting requirements because it also has to be completely in place. It cannot afford any data expansion because you're taking what might be a completely full hard drive and you're encrypting it. There might not be any space at all to write anything else. So
it's already divided into blocks, which helps. So.
Yeah, yes, it is. So it does sector-level encryption. And what it does is each sector is individually encrypted. There's no effect on other sectors. Sectors aren't blocked together. And the IV that's used is implicit in the sector number. So that's how get that. And what's done is a tricky method well, this was done for a while. I think I don't think it's being used anymore, but it's a nice design. What was being done, at least, was instead of encrypting block by block within the sector, to get good diffusion across the whole sector, there's a preprocessor that was run. There was sort of a diffuser that took all the bits in a sector, just scrambled them up, not in any really cryptographic way, just sort of spread them out. And then did an encryption, a block-by-block encryption on these spread out blocks. These mix, so it did this, got this mixing in. So if you change just one block, it's going to change everything in that sector. See, is there another? Okay, I guess not. I guess we're done for the day. Here's the sign-up sheet if people didn't get it. Thank you. And